So thanks for coming to this talk. I'm Zhibo Liu, and I'm a postdoc researcher at HKST. So this talk is about new attacks against DNN executables, and we have two speakers. I will introduce the side channel part, and my colleague Yanzhuo Chen will present the bit flip attack part. But due to the visa issue, Yanzhuo can't be a person, so we have a video recorded by Yanzhuo for the second part. And in addition to the two speakers, this work was contributed by the following collaborators. Yuan Yuan is currently a postdoc at ETH. Shui Wang is an associate professor at HKST. And Tianxiang Li, Siheng Hu, and Jihui Lin are security researchers at the CSI AI Red team. Okay, so let's get started now. So now in the age of AI, more and more cloud service providers like Google and Amazon have started to deploy their machine learning research outputs in their cloud. So machine learning models are available to users in the form of online services. And in such cases, providers deploy their private models in the cloud, so users can access these models via APIs. And the models can be viewed as valuable properties. For example, their designs and prediction parameters usually will consume considerable amount of computational resources and expert knowledge. However, recently we have also seen different works aiming at attacking DNNs, even when DNNs are deployed on the cloud, and attackers are restricted to access these models. So basically, these models can be, these attacks can leverage various side channels to steal model architectures, including operator types and hyperparameters. So they steal the model architecture from black box models deployed on the cloud. And after getting the model architecture, they can use model architecture to enable further attacks. For example, like model sting attacks and bit flip attacks. So if we know nothing about the architecture, such attacks can hardly be effective. And in this talk, by the way, we will talk more about bit flip attack in the second part. And meanwhile, we also observed that cloud service providers, they are exploring deep learning compilation techniques for in their resource sharing environments for private reasons. So this intrigued our interest because we knew that DNNs have been proven or to be vulnerable to side channels. So in this case, we want to ask, is there a risk of valuable properties being leaked via side channels when using DNN executables or deep learning compilation techniques? So this talk will answer this question. So we will first briefly introduce deep learning compilation and DNN executables. Then we will focus on the new side channel leakage that can be used to steal model architectures and new bit flip attack surfaces that can be used to control or manipulate model outputs. So first, let's look at the deep learning compilation techniques. So as we know, DNN can usually consume a large amount of computational resources. So we may want to deploy DNNs on various hardware devices for cost and profit reasons. For example, given a DNN model trained on GPUs, we can deploy it on cost-efficient CPUs. And in such cases, we want to leverage the performance potential of the target hardware. And as a result, deep learning compilation techniques are proposed to compile DNN models into DNN executables and to fully leverage the performance potential of target hardware devices. And basically, the deep learning compiler will automatically optimize the DNN model to generate efficient binary code. So the binary code can run on CPU as a native code. So basically, the DNN executable has the same functionality as the original DNN model. And also, depending on the target hardware and the input DNN model, the deep learning compiler will adjust or fine-tune the applied optimizations to unlock the full potential of the target hardware. So in this talk, we call such optimizations hardware-aware optimizations. So now, let's think from a security point of view. So what are the differences between DN executables and typical deep learning frameworks like PyTorch and TensorFlow. So in general, deep learning compilers provide specific optimizations for each operator in order to generate efficient, optimal low-level binary code. So there is no third-party linear algebra libraries used by DN executables. The DN executable runs in a standalone execution paradigm. So unlike in traditional or typical deep learning frameworks like PyTorch, where different processors may share the same PyTorch framework or the same linear algebra libraries. So DN executables do not share operators or memory regions with any other processors. Okay, so what's the influence of such a standalone execution paradigm? Does it make DN executable more secure against the side channels? So to answer the question, let's first look at existing attacks. So attacking DN models with side channels is not a new topic. Recently, many papers have been published and many works have been done to exploit different side channels to steal model architectures. And we surveyed recent attacks. And by the way, you can find a discussion, more detailed discussion in our paper on the website. And we have a link in the end of the talk where you can download the papers. So we surveyed the recent attacks and we categorized them into two major types, named as the physical access type, including electromagnetic side channels, bus snooping, and power side channels, and the remote access type, including Rowhammer-based model stealing attack and remote power side channels and cache side channels. So since remote side channels are more powerful and more threatening, so in this talk we mainly aim at remote access attacks. And here, due to the time limit, here we only briefly list the major limitations of recent remote side channel works. So the Rowhammer-based model stealing attack is limited by its low efficiency because Rowhammer is quite slow. And it currently only targets quantized model. And remote power side channels relies on system-level interfaces, and it requires user privileges. And the cache side channel, which is one of the most common side channels, it requires shared memory regions in order to accurately monitor program execution. Okay, so all the attacks mentioned here aim at typical deep learning frameworks like PyTorch. So we want to ask, can they be applied to DN executables? And here the short answer is no. As I mentioned earlier, the DN executable has a unique standalone execution paradigm. So there's no shared memory for accurate cache side channel attacks, and there are no third-party libraries for attackers to pre-analyze and locate sensitive functions. So as a result, none of the existing attacks can be applied to DN executable. So the next question following that is using deep learning compilation a more secure way to deploy DNs in the cloud? And unfortunately, we will show that DN executable is still vulnerable to cache side channels. So we first took a close look at the cache access traces of compiled DN executables. So to do so, we collect the cache traces simulated with Intel pin, which is a binary instrumentation tool. So we do so to avoid noise and to make the traces easier to understand and recognize by human eyes. So as shown in the figure, in which each row contains 64 pixels. Each pixel is a cache line, so there are 64 cache lines in one row. And the dark pixel means the cache line is visited by the victim, and the gray pixel means it's not visited by the victim. So we log a row, which is the state of L1 cache after a short interval. We do so to mimic a typical prime and probe attack. And as we can see, there is a pattern that occurs repeatedly in the cache trace. And more than that, different operators will have different cache access patterns, thus giving us an opportunity to distinguish different operators. Okay, so now we know that there might be some kind of patterns if we try to monitor the DNN with typical cache side channels. But why is that? To answer this question, we conducted a detailed analysis and found that compiler optimizations lead to this phenomenon. So before explaining how optimizations can influence cache activities, in this talk, we first briefly introduce two major optimization strategies employed by deep learning compilers. So one of them is blocking. As shown in this figure, in figure A, if we naively compute the matrix multiplication, we will sweep the matrix many times and encounter many cache misses because the size of cache is limited and it's much smaller than the size of the matrix. But if we split the matrix into blocks, as shown in figure B, so the memory sizes are restricted in a small region, leading to better memory locality and faster computation. And another optimization I'd like to introduce is vectorization. So modern CPUs provide the SIMD extension. SIMD instructions can read consecutive memory and compute multiple data in parallel. So to leverage such instructions, deep learning compilers will rearrange or reshape the memory layout of model parameters. So as shown in the figure, overall, what we want to say is that optimizing DNN computation is not an easy task, and some deep learning compilers will even use machine learning-based approach to automatically fine-tune the optimization and to decide how to block and how to reshape the memory layout. Okay, so what are the consequences of these optimizations? Here we provide a code example. And by the way, you can skip details of the code and just skim over it. And we have this example in our paper on our website. So here the point is, before optimization, the convolution operator has a naive loop structure. And basically, it will sweep the input matrix many times. Thus, such code shows the memory locality, and it's slow. And after optimizations, some loops will be split and permutated, resulting in unique loop structures. So in this example, some loops are split into outer and inner loops for better memory locality. And such optimizations depend on the hyperparameters of the operator. So in this example, the inner loops will even be unrolled for performance improvements. Okay, so now we know that compiler optimizations will largely change the loop structures. So what we want to say here is that each operator will be specifically optimized according to its hyperparameters. So that means they are optimized with different optimization factors like the size of split blocks and the shape of optimized memory layout. So as a consequence, these show distinct loop structures in the binary code. So if we can determine the binary code determine the loop structures in the binary code, we can distinguish different operators. It's like a fingerprint of operators. And more importantly, by recognizing or distinguishing different operators, we are actually recovering model architectures because models are made up of different operators. However, as I mentioned earlier, we only have remote access to the model. We only can access the model via APIs. And we cannot know the loop structure in the low-level or binary code, so it's impossible. Thus, in this work, we depict the loop structure in an implicit way. So such DNN usually involves massive computations and memory accesses. It will result in distinguishable cache activities that can be captured with typical cache set channels like Prime+Probe. So in this work, we depict the binary level code structures with the inner loop factor and the outer loop factor. So here, the inner loop factor denotes the pattern in the cache traces, and the outer loop factor denotes the frequency of the pattern. Or more straightforward, cache access patterns depends on the operator. And according to our analysis, there should be a one-to-one mapping relation that can potentially be exploited by the attacker to infer operators in the victim model. Okay, so up to now, we have uncovered a potential attacking surface in de-executables, as shown in this figure. Prior works usually start with manually locating sensitive functions in third-party libraries. And differently, we reveal that hardware-aware optimizations can introduce new side-channel leakages. So the problem now is, how can we exploit such a potential side-channel leakage and confirm our conclusions? So based on our findings, we propose to extract identifiers from two perspectives with machine learning models. So more specifically, we extract the observed pattern with a feature extraction model as the in-the-loop factor. And we extract the number that the pattern repeated with the trace segmentation model as outer-loop factor. Then we combine the two perspectives or the two factors as the identifier and match the most similar candidate in the identifier database. So given the candidate, we can know the operator type and the hyperparameters because all the information are logged in the database. So in the following slide, I will skip technical details because we use standard models and standard techniques. But no worries, you can still find our technical details and released code in our paper and website. So for the first part, we use contrastive learning for the feature extraction. So basically, we view a trace space as a one-channel image. So our idea is that trace spaces from the same operator should have similar feature vectors. So in this way, we can train the model in an unsupervised way and extract features from cache traces automatically. So that's the basic idea. And for the second part, to get the outer loop factor, we segment the trace with a recurrent encoder-decoder model. So it's quite a typical model used in AI community. So this model tries to compress and recover the input matrix. So the idea is that frequent normal patterns can quickly be learned by this model. So if the model fails to recover the input matrix, it indicates that there might be an anomaly in the trace. And basically, this encoder-decoder network will sweep the trace to find the locations of anomalies and figure out how many times the pattern is repeated. So basically, we view the boundary of two patterns as an anomaly. Okay, so that's the basic idea of our attacking framework. So how well does our method work in real cache side channel settings? So in the evaluation, we choose ResNet and VGG as the victim model, and other 28 models as the database. So all models are compiled with two state-of-the-art compilers, TVM and GLOW. And we also evaluate the proposed attacking framework with L1 and LLC cache side channels separately. So here we provide an example to illustrate steps. So given a victim DNN executable, we collect cache traces with typical prime and probe attack, and then feed the traces to R2. R2 will output the mode architectures, including operator types and corresponding hyperparameters. So such information can be used to reconstruct mode architectures. And as for the results, overall, we can achieve about 90% accuracy for TVM bandwidth and over 70% accuracy for GLOW bandwidth in the L1 setting. The results are not bad. However, for the LLC setting, which we achieve above 90% accuracy, which is even better than the L1 setting. So this is beyond our expectations because generally we believe that LLC attack is more challenging than the L1 cache attack. So why is that? We conduct analysis to interpret why the LLC attack shows better results. And we find that some compiled operators are not optimal, which means the binary code shows low memory locality and low cache hit rate. So the next question is, why low cache hit rate will prevent attackers? Again, we'll provide an example here. And you can find example in our paper and the website. So so no need to worry if you didn't get the idea here. So in short, the point is this loop, which is the core of a convolution operator, this loop will read 64 KB of different memory in total. However, the L1 cache in our setting is 32 KB, which means the code will be self-competing. It will evict its own data from L1 cache, and it never leverages the benefits of an L1 cache. So as a result, in figure A, from a attacker's perspective, such cache access traces are featureless because all cache lines are visited by the victim. So such traces are non-distinguishable to the attackers. So again, here is a dilemma between performance and security. If we optimize the code, there will be actual leakage. But if we do not optimize the code, there will be performance slowdown. OK, so that's all for the cache session part of this talk. But it's not over yet. My colleague, Yanzuo Chen, he can't come here in person due to the visa issue, but he has a recorded video to show a novel bit flip attack against DN executables. So let me first briefly introduce Yanzuo. Yanzuo is a fourth-year PhD student at KUST, and he's currently visiting South Tech. And he does research on system security. And his works were published at top-tier security conferences like NDSS, CCS, and SP. And although Yanzuo can't come here answer questions now, he would be happy to answer questions via email. So please feel free to email him or me. OK, so I guess it's time for Yanzuo's talk, and we can play the video now.
I'm Yanzuo, and I'll continue to the second part of our talk. Now we've talked about stealing stuff out of DNN executables. A very intuitive question that arises now is, how can we use what we know about the models to attack them? Like control them and make them do bad stuff. For example, we'd like to make a classification model see a ninja when looking at this picture. Or in a world where ninjas don't exist, maybe it would tell you that you've committed some serious crime when you haven't. So we know there are existing attacks to do this, like adversary examples, data poisoning, backdoors, etc. But there's a problem with them. These attacks are all like optimization problems with respect to model weights. And model developers can also use optimization methods to augment the models in defense. But as systems research people, we'd like to know whether we can attack the models in a way that bypass these defenses. A way to attack them through a dimension that they simply can't defend against. So, could we do that? Recall that we've just exploited CPU microarchitectures to steal model architectures. And we still want to come back to a low level like this. So looking aside the CPU, we see what's been staring at us the whole time. DRAM microarchitectures. There's been this Rowhammer attack which was discovered in 2014. This is a hardware vulnerability triggered using only software. Basically, when you access the memory in some specific pattern and you do it so fast, you trigger current leakage between DRAM cells, and the data bits in those cells can get flipped. Rowhammer has been and is still a very real threat. Over the years, researchers have successfully broken DDR3, DDR4, ECC memory, and recently also got DDR5 squared away. So it's really a die-hard vulnerability. You also see all kinds of applications like privilege escalation, cross-VM attacks, and attacking victims through the browser and JavaScript. And actually, researchers have also tried Rowhammer on DNN models, and they found it pretty effective when bits in model weights are flipped. But there's a problem. They need white box knowledge of the victim models to calculate the gradients and figure out which bits to flip. But what if we don't have that knowledge? After all, weights are often confidential, right? Okay, so what can we do if flipping model weights are off limits? The answer is actually in the name DNN executable. What's inside these executables? Code. All compiled machine code for the DNN operators used by the model. If we can flip bits in there, we can probably change the model's behavior. Okay, so to recap our setup, our objective is to destroy model intelligence with bit flips. For example, to make them become random guesses. And as attackers, we only know the model structure and how to compile the model to get the victim binary, because model structures are often published. And if not, existing tools can also help us recover them. Importantly, we have no access or knowledge or whatsoever to the victim model weights. Under this setup, the most important problem we want to solve is, how do we figure out which bits to flip? Note that we are not trying to tell you how to flip those bits. There's been ample resources on that. Rather, we tell you how to find vulnerable bits to flip with very limited knowledge. Here's what the attack flow looks like. And basically, it's the same for all bit flip attacks on DNNs. The attacker first uses whatever knowledge they have to construct some local model so they can examine and play with it however they want. And once the attacker decided which bits to flip, they launch the real attack on the victim model. Here's a comparison between existing attacks and ours. In existing attacks, the attacker knows everything about the victim model. So they calculate the model gradients locally to find the most vulnerable bits to flip in the model weights, which makes the calculation and prediction results of the model become essentially broken numbers. On the other hand, we only get to know the model structure and how to compile the model as the victim did. No victim model weights, no victim training sets, or things like that. We then look at the machine code in the compiled binary and try to figure out which bits to flip. Note that we are flipping bits in the code region, so we're actually changing the instructions in the executable, not the numerical weights. Great, now we have our setup. It's time to get to hacking. So the first idea that comes to mind is, can we just try stuff until it works? This is very intuitive and straightforward after all. So because we already know the range of the code region in the victim model, we can randomly choose a bit inside that region. And we flip it. And we check how the model's doing after that. Here we are only flipping one bit at a time, because if just one bit is enough to ruin the model, then we don't need more. A simple and optimistic plan. And surprisingly, it turned out really bad. The attack success rate was only around 2%. This means that if we are to choose a bit randomly to flip in the victim model, we would only successfully downgrade a classification model to a random guesser around 2% of the time. What happened in the other 98% of the time? We pulled some statistics and found that most of them led to crashes, which we don't like because it just stops the program. And other times it's like nothing happens at all. This can be the case if, for example, a bit on some unreached code path is flipped, or when the disruption is so small that it's too far away from our goal of creating a random guesser. But those 2% of bits also tells us something, because we now know that random flips have a chance of 2% to succeed. But what if we locally collect all those bits first and try only those bits on the victim executable? In an ideal world, that should result in an 100% success rate. So To do that, we compile and train the model on an arbitrary dataset. We can't use the same training set as the victim because we don't have that knowledge. After that, we scan through every bit in the code region and record which bits are one of those 2% useful bits. Once we have that data, we can then try these bits one by one on the victim executable. And the result was kind of okay. It kind of worked, and our attack success rate is now at around 45%. This means that after our local scanning step, we are now 45% confident that when we attempt a flip in the victim executable, it will cause a complete depletion of model intelligence rather than other unwanted results. You may be wondering, if we are already trying the useful bits only, why isn't the ASR 100%? Well, that's because our model doesn't have the same weights as the victim. If we can construct the identical model with identical weights, then we can come up with perfect attack plans, just as existing attacks do. But this result is actually telling us something more, that the vulnerable bits may be transferable. More specifically, our model has different weights from the victim model, but the vulnerable bits in our model still have a 45% chance to also work on their model. And this is a very interesting result. Maybe we can use it to do even better in finding bits to attack in the victim model. So how do we make use of that lesson? In the previous attempt, we were using a surrogate model trained on an arbitrary dataset. And that is perhaps the best we can do, because we have no idea what the victim's training set is. But think about this. What if we train our model on more datasets? Do the vulnerable bit scan for each and get the intersection of the results? In other words, we want to find vulnerable bits that could successfully attack all our locally generated executables trained on different datasets, and hope that they will also transfer to the victim executable. To sound cooler, we call this transferable bits Superbits. Okay, so that sounds plausible. We just need to answer one more question before we can start trying. What datasets do we use to train our local models? Well, our answer may sound somewhat unexpected. Just use random noise initialized with different seeds as different datasets. And spoiler alert, they work pretty well. In fact, there's been some study and research in the machine learning community on the effect of random datasets. And they found that in phases like pre-training, these random datasets actually regulate the model weights to gradually resemble the weights in well-trained models. So in a sense, they contribute to the training process. Another advantage of using random datasets is that we don't have to consider biases now. For example, if the victim trained their model on cat photos, but we're using X-ray images to train ours, the distribution of weights may be far away from each other. And using random datasets is more of an unbiased choice in this sense. So we went ahead and generated many executables on different random datasets, which we conveniently name as fake datasets. And here are the results. If we use 10 of those datasets to find these superbits, we reach an ASR, or attack success rate, of around 70%. We are now 70% confident that the flips we try on the victim executable will do what we want. This is much better than what we began with, like 2%, or what we did in our previous attempt, 45%. we are pretty satisfied with this result. So it now sounds like something that we can really try in a real-world experiment. So the next thing we did was to see how our attack worked with real-world cases. To do this, we built our attack on Blacksmith, a state-of-the-art rollhammer toolkit on DDR4 memory. We tried the Superbits we found on a wide range of victim executables, and they worked really well in all cases. The accuracy changes here show that all models are now random guesses, so they are equipped with the eyes to see the beauty of ninjas out of panda photos. And there's exactly 0 crashes in the process, meaning that the system admins won't see a crash report somewhere in their system logs. But the most important metric here is the number of flips, which is on average 1.4 flips to completely deplete the intelligence in all models. In case you are wondering what that means exactly, take a look at this table from DeepHammer, a state-of-the-art attack targeting model weights. On average, they need 12 flips to achieve the same attack performance as ours, and we only need fewer than 2. Not to mention that they also need to know the victim weights, but we don't need that at all. Yeah, so we're pretty amazed by the results, and out of curiosity, we also did some case studies to find out why this attack works. But unfortunately, we won't have the time here to really talk about that. But we can still look at one simple case. So in this case, you can see the operand of the compare instruction has been changed. And this is actually a check that determines whether the current thread is needed for computation. After the flip, it's like every thread in the thread pool now thinks that it's not needed anymore for the current computation. So all computations are skipped and the result is left uninitialized. So through this case, you can see it's not really possible to defend against this kind of attack with, for example, optimization methods, and that's why new defense paradigms are needed. If you want, you can learn more about our case studies and actually everything else about the research at that link. So before we end, we have a few takeaways for you. We've proposed DeepCache, where we found deep learning compiler optimizations essentially gave away model architectures. We also found DNN executables to be 6 times easier to attack with bit flip attacks. Therefore, we would really like to see more security research on DNN executables, either on the offensive side or the defensive side, as that would surely make the whole ecosystem more robust. Thank you.
Okay, so now I'm open to questions regarding to the first part. And yeah.
Hi, Scott Constable, Intel Labs. I have, if it's okay, I have one question on the first part and one question on the second. At least on the first, did you also consider cache attacks or other kinds of side channel attacks against DNNs that are compiled by JITs? And then for the second part, I'd like to better understand the threat model, because it seems like you'd need to have a local attacker co-located with the model, and I'm questioning how realistic that is in practice.
Okay, so for the first question, sorry, can you repeat the first question?
Did you also look at side channel attacks against DNNs that are deployed and compiled using JITs rather than deployed as a monolithic executable?
So we didn't try with JIT, but I think the idea is general, because if you use some optimizations regarding to changing the loop structure in the binary code, so this attack should be work. And as for other cache side channels, I think it's possible to use other side channels because so in this work, we didn't create or design a new cache channel attack. We use existing side channel. We use Prime+Probe. So we noticed that there are many other more advanced side channels like Prime and Scope. So such new side channels can also be used to collect cache traces or to just try to digest and extract some information from the cache traces. So yeah, I think it's possible. And for the second part, so I think the answer would be similar because we didn't try to design or propose a new row-hammer attack. So we use the same assumptions of existing row-hammer attack. So we can use the same techniques used by their works to let the victim and the attacker to locate in the same hardware environment, I think.
Okay, thank you.
Thank you. Okay, so we don't have enough time. So if you have any other question, you can feel free to email us. Yes, thank you.